Yeah, it should be a live video. It's draftphysics.com, debatephysics.com, also video presentation. So just more of the same. Yeah. So it's not what we need a new presenter. We need a new audience. Yeah, we need more people to get involved in the conversation, and that's just not really under my control, unfortunately. Not that if it was under my control, I would handle it perfectly, but just it is just irritating. Anyway, that you're subjected to this difficult task of becoming relevant to conversation in the world, and even if you have a decent enough argument, yeah, forget it. But anyway, enough of that complaint. So this is just a simple description of how physics made the big mistake. Okay, and it's just such a ridiculous big mistake that you'd have to argue, well, they really don't have an excuse for making it just this big a mistake, on something that's just so easily understood. And it just hits at the credibility of physics. That if they can't get this kind of stuff right, then what hope do they have on the real complicated subjects, I guess, would be the simple enough argument. So obviously you could move these two things, could have the same mass and the same velocity, okay, just an mv. And by the way physics measures energy, they would say that because the pointy arrow will go much further, okay, a much greater d distance, therefore somehow it has more energy, okay. And it really doesn't, but it has a practical kind of extra energy, in the sense that obviously if you want to get a certain thing done to the surface, this, in terms of penetration being important, like say you're trying to get to hit the heart of an animal. Well, you don't want to just go an inch away from its heart. You want to go right through it and cause all kinds of hemorrhaging and whatnot. So you can see where it has a practical effect. Tank weapons are made very precisely to have very hard tips and be able to melt the iron to get through the tank, blah blah blah. So yeah, there's lots of ways to engineer your mass and your velocity so it'll do more of what the desired effect is. All right, and in this case, the idea of the pointy arrow is just kind of obvious, in the sense it's going to push stuff sideways instead of pushing stuff forward. Because if it pushes it forward, you can understand it's got to do both functions. It's got to push it forward, and then eventually it has to push it out. And that sort of happens with water waves. The impact force goes through the water. The water is uncompressible, so the pressure goes way up, and then the water can't go down because down is the hard ground, so it ends up going up. Okay, because that's the only place there's a lower pressure, and that's work. Having to change your direction is often going to require you to do work, and so the momentum of the object is diminished, because you're basically saying, instead of having a nice straight path for the energy, it's going to start going in directions, okay, that aren't forward. Okay, so it's going to be creating, you could argue, heat or deformation or some other sloppier motion or movement of objects. So it's going to be moving objects in all kinds of directions that aren't helpful to your purpose. And clearly just more friction. The flat surface is a real high friction. The pointy surface is less friction, less contact for less time. All of those rules apply. So it's just, frankly, it's grammar school, okay? You should only have to explain why pointy arrows work better to kids, and you should only have to explain that it's not energy, okay? There's not more energy in the pointy arrow, all right? There's just more effectiveness. So you could use the word E for effectiveness. It's more effective at a specific purpose, but it doesn't contain more energy, and it doesn't make more matter move. So the MV will be the same in both these cases. It's just going to look different. Okay, what masses are moving will be different. Different things will be moving in different directions. And that's the only difference you're going to have in these two circumstances. All right. So that's, put a box around it. It's a pretty hard, clear, factual thing to state that there's no extra energy in this pointy one. It doesn't actually do more work. It doesn't actually accomplish transfer of more energy. It transfers exactly the same amount of energy. It just transfers it differently. All right, now I'm going to make the argument that speed is exactly like this pointy arrow. It's doing exactly the same thing. It's just creating an advantage for circumstances. So depending on what your circumstance is, it's an advantage. So you could have some task to perform, like there's a river, okay, and you want to cross it. The simple fact is the faster you can get through the river, the less work you have to do to stay, unbent in your path. So if you go slow, you get pushed way downstream and you have to walk all the way back to here, right? You go fast, you don't have to waste any energy, you don't have to do any of that stuff because you evaded the force essentially. So you can clearly understand that depending on what speed I go, I'm going to do a lot more work because I'm going to have a lot more of this force. Okay, the force is completely time dependent in a river. There's a certain amount of it flowing per second past the point, and the fact is the longer I'm in that flow, the more it's going to push on me, the more it's going to create this problem of taking me where I don't want to go. So it's the same kind of argument, is that you have to conserve all of the energy. I mean, it's the, but the point is you'll use the same energy. See, this longer path is also, intrinsically a slower path, because you're doing it, in straight line bits, sort of, you could understand. So you're going forward, but you're getting moved sideways. All right, so you could argue that it could take you the same amount of time, but it's really not going to. You're probably going to end up taking a little more time. Now, if it was a gravity argument, it would be the same, but let's not get lost in those kind of details. But the simple truth is it's the amount of how your velocity will dictate how fast you get across. And you're obviously going slower to be dragged by the stream, so this has to take you a longer amount of time. And if it's a longer amount of time, you're fighting more force. And so that's the key difference between going fast and going slow, is you're just going to fight more force. So if I did make it just a gravity argument and you're going by a gravitational body, you can just understand the faster you go, the less absolute work you'll have to do, and the slower you go to stay on your course. And the slower you go, the more work you're going to have to do to keep yourself getting to point B, if that's what the objective is. Well, this pen has about had it. Yeah, so I can erase that and start over. Okay, so yeah, I could have two different objects that have the same momentum, a big object and a small object, and they could have the same mv. All right, so one's a larger m, and I guess I could make the m bigger, and a smaller v, and the other one's going to be a small m and a big v. And the fact is that this one may be more effective, okay, because of the higher velocity at accomplishing a task, especially if the task is getting through a gravitational well or something. It's going to be able to go through it much better, more effectively, and only because of the high velocity. So, if I was to redraw that correctly, so you could understand that the heavy object ends up doing something like this, and the light object with the same energy, same mv, same momentum, ends up doing that. Ends up straight. And so it's defeated the force. So you can understand that if something's small and moving fast, that, let's say it's interacting with electrons and protons that are in, relationship to each other based on a speed of light force that's connecting them, okay, that's creating pressure between them. And you could sort of understand that that's going to be the same thing as like magnets holding things together. And if I can move the magnet quickly, then it won't feel the force of the other magnet, because it takes time for the magnets to communicate. So when two magnets are facing each other, one magnet, okay, another magnet, the force between them, okay, is completely controlled by speed. So if I can get this magnet to move really fast, it won't even notice this magnet exists. The force will be kind of minimal. And the slower I move them, the more likely it is they'll smash together. So it's the same argument as the gravity argument. And so velocity, again, can increase your capacity to defeat forces that are tying things together, sticking them together. So it's almost like defeating friction or something else, where doing it quickly works better than doing it slowly. Hitting it with enough energy to break it free quickly will be less expensive than you trying to slowly drag it out of its friction. Lots of other examples that I'm not thinking of at the moment, but you could talk about ice or stuck in the mud or some other circumstance where you can understand that if you can get your velocity high enough, you can reduce the friction and make the whole thing happen much overcome the obstacle, let's just put it that way. And that the key ingredient is having enough speed to defeat what you're trying to defeat. Probably mud's a bad example, but So the point is that you can understand that speed is just a gimmick. Just like the pointy arrow, it's not about how much energy it actually has. It just has to do with that there's advantages to breaking things with velocity. Velocity breaks surfaces, especially. And like an arrow, it creates a way to penetrate something and deeper and further, okay, with the same amount of energy. By just changing that mass to velocity ratio, you make it more effective. So the simple argument is that the recoiling gun, if I was to, if there was a way, okay, where I could just attach the gun and shoot a bullet, and then I was able to have the bullet attached to me and then shoot the gun, those two events will be the same for me. The recoil will be the same, because I'm just shooting it's just the gun that's moving. It's just the mass of the gun, the half of a momentum created by the explosion. I'm going to get half of it. And so in either case, I'm going to get half of it. Now, it's not going to be exactly half, because the truth is probably the bullet gets a little bit more of the energy because it moves more liberally. But regardless, it's close enough to half that it doesn't matter. So it kind of just proves that it's not about creating something that has more energy. It's just about the fact that, in one form, it's going to look like something more. So when you do the experiment where you actually let the bullet fly into somebody's head or something, yeah, it's moving matter, but it's really just moving the same amount of mass that will be moved by the recoiling gun, and all you're doing is spreading it over a larger surface, so you're making it less dangerous to the molecular structure. You're creating a much bigger surface area to absorb the movement, and therefore the movement doesn't fracture it. Where, obviously if you had some tension, like water tension or something, there's a big difference between spreading it over a large surface and then spreading the same force over a small surface. This will be more likely to burst than applying the same amount of force over the much larger area. So, those again are kind of grammar school arguments that can be understood. That it just depends on how much surface area there is. Now, it's like even a pin. You can push a pin into a balloon, and if you're very slow about and careful, you won't burst the balloon. But any quick movement, you're guaranteed to pop the balloon. So, those are just simple principles that speed has advantages to accomplish certain tasks, but it's not intrinsically more energy. It's just more effective at doing certain things to certain substances. And that's it. Now, I'm arguing that the fact that physics is fooled and that it actually thinks there's some reason to create this silly formula, okay, where you have this squared component claiming that fast things, small fast things with the same momentum as big slow things, that the fast thing, even though it's the same momentum, has thousands of times more energy. So they say the bullet will have 2,000 joules of energy, and they'll say the recoiling gun has only 2. Okay, gigantic difference in what they're claiming the distribution of the energy is. Now, that's clearly in violation of Newton's third law, so it should be erasable, okay, as a fact. It should just be, oh, okay, we can't do that. I mean, it's violating the third law. What's the point of it? You can't say that. You can't claim that, the action and the reaction aren't the same, because that's what the law says. So say you don't agree with the law, but don't sit there and pretend you're defending the law with an example that clearly illustrates the law doesn't work. So it's all quite lame. This argument that there's actual joules 2,000 times. So again, they're saying that one atom moving 1,000 miles an hour, okay, is 1,000 times the energy, okay, of 1,000 atoms moving 1 mile an hour. That's their claim. And it's, clearly, superficially, you could look at these things and say, well, that looks so much worse for the human being, getting hit with the bullet versus getting hit with the recoiling gun. There's no doubt that the two events are going to be completely different. Your surface is, can control the slow impact of the heavy mass. It can't control, it can't stop the, very small mass moving at a very high velocity. All right, but it's the same transfer of energy. If you're going to talk about conservation, the only thing that's going to be conserved is the MV, and it'll always be conserved in the sense you'll always be able to find it. Now, another thing physicists do all the time is they say, well, the kinetic energy isn't conserved in inelastic collisions, as if it's some kind of rule that they just make it disappear. But they're claiming conservation. They're just claiming it's doing something else. Conservation doesn't mean it only does one thing. I mean, heat is conservation. Any place where you're seeing the energy in some other location, that's conservation. I mean, they clearly know that if I break something, if I hit a glass ball, and I break it into little tiny pieces, they don't sit there and say, oh, the momentum or the energy wasn't conserved. No, they just add up all the little pieces. So they claim it's conserved. Yeah, it's not conserved in a straight line anymore. It's not conserved in one object moving anymore, but it's conserved in the sense they know they have to add up all the movement and figure out, what went in also comes out, that it is all the energy remains in the universe. That's what conservation means, is that it's still moving in the universe. You've conserved the existence of the MV, the motion. But you can't conserve MV squared, because obviously every time you convert a heavy thing on one side into a light thing on the other side of the lever, you'd be making free energy. And you can't make free energy. Obviously, we'd have it if you could. So that's the most obvious reason why it's kind of silly to defend the kinetic energy theory, because it basically is a free energy theory. Alright, see if I can get to this pen without something falling. Purple. See if the purple works. Yeah, so these are all kind of lame. Yeah, that's quite dark. Me likey. Alright, so that's where I wanted to start. So I'll play a Shakar Ramam something or other. Shakar from Yale, and he did these like 20 years ago, so it's a long time now. So anyway, and it's all it's all formulas. I mean, he draws a few pictures, but it's all just basically his videos are all formulas, and there's no labs, there's no experiments. There's just talk, and that is unfortunate. But so we're at a point in that video I'm going to show you, where he's doing the equation for the free momentum equation. Where when something goes in the opposite direction, somehow you subtract its motion, so it doesn't count. So somehow you could, I mean, it's really this bad. I mean, really, I shouldn't have to say it, but I mean, it's this bad. Is they're basically saying I could hit two objects, all right, and that they would leave and have components, okay, clear components in two different directions. All right, they're going to have a clear vector this way and a clear vector this way. And the argument is those don't cancel. You can't cancel those momentums, those vectors. They're real. They're part of exactly what the total motion of the object is, and there's just no cancellation. So this idea that because, and obviously I could do this experiment very subtly, where I could probably get these two objects to almost move perfectly this way, with just the tiniest bit of motion in that direction. And, and clearly if I hit a stack of balls, I can get all kinds of directions out of them. So, and we know that, if one ball's going this way and the other ball on the other side is going that way, you can't cancel those momentums. You can't. Well, it'd be better if the picture wasn't on top of the drawing. Be a lot better. Okay, so this is what I was trying to illustrate. So this is your initial MV, and the fact is this MV plus this MV is going to equal, equal sign, this MV. Both of these together, you can't cancel them. You can't say because two objects are going in opposite directions, you're going to cancel and you're going to get a right answer, because you're not. Because again, you can create a circumstance, probably even clearer would be, I mean, you can really do this. I mean, I did play pool as a kid. Had a pool table. First thing I bought with my newspaper money. Anyway, yeah, my father made me buy everything. Anyway, it's just, get a job. You're 10 years old, and it's like, get a job. It wasn't good for me, frankly. Every single day, rain or shine, snow, sleet, doesn't matter. Go walk 4 miles and carrying 50 pounds of papers. Anyway, I have a lot of little gripes. Yeah, they're little though, but I have a lot of them. All right, anyway, so if you did this experiment, that this is going to leave with a certain MV. All right, and these two are going to leave with MVs in opposite directions, and so you can't cancel these two forces. That you're going to add up all these vectors, and they're going to have to add this. They're going to have to add up to this momentum vector. You can't cheat. And so we know just from a simple experiment like that that this formula that Shikar has on his blackboard just can't be true. I mean, it can't be the truth, because it creates this problem of saying, somehow you can cancel motion, that motion this way undoes motion that way, and it can't undo it. It's just wrong. So anyway, the only reason though this video is because he's going to show a ballistic pendulum, and he's going to do such a lame job of it, that it deserves. But this is the reason why they can get away with it. Is the point I sort of want to make. Is the reason why they can get away with this crappy physics is because they do just gloss over all the details, and there's just huge, gigantic details here, and they shouldn't be glossed over. All right, so I guess I might as well do it first. So I've done, I've drawn this so many times, but the ballistic pendulum, simple enough device. But the argument they're making that somehow all the momentum is conserved when it's clearly not all the momentum is conserved. It just doesn't happen in the sense of conserved in being in linear motion. So we have a linear motion here. We're not going to count the bullet spinning or if it was rotating or something else. We're just going to say it has a linear motion in 2,000 joules of energy. And an MV that equals 2. Okay, so the kinetic energy says there's 1,000 times more energy than the MV says. All right, and the fact is this thing's going to move, okay, with a linear velocity. Okay, and that's what I calculated here, the linear velocity, and it's only going to get the 2. Okay, so the 2 joules will be transferred. Now the fact is it won't. It'll be something like 98 or 95, percent of the MV. So it won't be all of it. So the fact is you're going to just say, okay, well, where's the rest? And so it has to all be conserved. So the fact that it didn't be converted into linear motion doesn't mean it's not anywhere. And it means that, yeah, clearly it's in motion inside the ballistic pendulum. The gel got displaced, it moved in directions, and ultimately all of that energy can't leave here as anything other than heat, some sort of radiation. Now it's going to move, let's say it vibrated a little bit, so it's going to move some air. Technically that won't be heat. It might be some other kind of radiation. And there's going to be other things, besides infrared. It's going to create maybe a radio signal for a minute. It's going to create some other signals because it's going to be having some internal motion, and this stuff's going to be bouncing around inside of it a little bit, force, lines of force, if you want to call them that. But anyway, that the 5% is here. That's what it's going to be leaving as. Is that it's going to be leaving as some kind of radiation into the atmosphere, heat probably, mostly. But the fact is you lost, 99.94% of the kinetic energy. So you didn't get any of the kinetic energy. I mean, frankly, none of it. You only got the momentum portion. This here, this 0.06, that's this 5% of the momentum. That's all this is. So, it's kind of clear, that, yeah, that's the only part that the small percentage of the momentum was lost. That's also revealed in the kinetic energy, in the sense that the linear motion is a little bit less than with the momentum. But it'd be 100% if I didn't make heat and I got all of the momentum. Then I would have lost 100% of the kinetic energy. And the whole thing doesn't make any sense, but how can just the kinetic energy make heat? Well, the momentum's going to make some heat too. And the fact is that little percentage accounts for the whole friggin' equation. So this is a figment. There's no 2,000 joules of kinetic energy, but you can't collect them. Now there is no, like I said, if you measure the heat, it's going to be a tiny amount of heat, 0.5 joules or something less than that even. Very small amount. And won't be anything like this gigantic 1999.06. It's not going to be 99.06 joules. That's what's missing. 1999.06 joules is what's missing. That's what they're claiming is in here. So, I mean, isn't that just, come on. How does anybody believe this nonsense? And if they can't get this right, this isn't that complicated, this mechanics. To argue that somehow you can make 1999.06 joules of heat with just 2 joules of momentum is too silly. Okay. And yet I have to make these arguments for years. But you can understand, if they can make this kind of glaring mistake, they can't get energy right. They're physicists and they can't get the concept of energy right. They can't understand that they're being fooled by the pointy arrow. They're being fooled into thinking light things going fast that have the same momentum as a heavy thing going slow, that somehow the light thing has thousands of times more energy. Could be 10 times, could be 100 times, could be 1,000, could be 10,000, can be 1,000,000 times more energy when you start getting to the movement of electrons and protons at very high velocities. So that squared function has huge implications. And to get all of that wrong, and provably wrong in the sense that none of these foundational experiments are consistent with their theory, none of them conserve the momentum if they conserve the kinetic energy, it's just so glaring that why are you trusting them on any of these other subjects? But I really have to get you to accept that this is so obvious. I shouldn't have to do this over and over again, because it doesn't work with levers, it doesn't work with gears, it doesn't work with hydraulics, it doesn't work with a ballistic pendulum, it doesn't work with spaceships, it doesn't work with pulleys. It doesn't work ever. No matter what the experiment is, it fails to be consistent with the outcome. Again, you just go the simple mythbuster kind of argument, but I mean, frankly, it's just a coincidence that the experiment failed. I mean, a 50-mile-an-hour car, 100-mile-an-hour car, same car, crashed into the same brick wall, okay? And the 100-mile-an-hour car is only twice as crushed. Not 4 times, not even close to 4 times, not even 3 times, not even close. And then the whole argument that somehow if I made this 10-mile-an-hour to 30-mile-an-hour, that somehow it's going to be 9 times more damage to the car. 9 times? That I need 9 compressed springs to move something 3 times as fast? I mean, really, that's worth illustrating again. I mean, do I need to say any more, right? Okay, so they're saying I need 9 compressed springs, okay, to make an object move 3 times the velocity, 3 velocity. I need 9 springs. I need to compress a full spring, right? I need to compress it, not just 1 unit for 1 velocity. That's going to give me 1 velocity right there. Just a fact. And then they're saying I have to compress it 2, 3, 4 times to get twice the velocity. And then I have to go 5 more all the way to here, 9 to get 3 times. I have to compress the spring 9 times the weight to create 3 times the velocity. I have to argue this with people who think they're literate, intelligent, reasonable. You think you're a reasonable person, right? Do you think that's a reasonable outcome? That's their prediction. They say explicitly that's what it requires. I cannot make something go 3 times the velocity unless I put 9 units of energy in. That's what their theory explicitly says. And like I said, it just gets worse and worse. 16 times, 16 springs to go 4 times as fast. 25 springs. Do I actually have to draw them all? Right? 25 springs. 25 springs to go 5 times as fast. Come on. It's the explicit requirement. It's what their theory demands be true. It can't not be true and their theory be true. It's a catastrophic failure if it fails this experiment. This is a test. And obviously, clearly, it fails dismally. So if you're going to take Einstein seriously for anything, I mean, he wasn't the one who said it, but I mean, obviously, you just need one circumstance where your theory doesn't fit the evidence, and you're done if you don't have an excuse for that lack of fitting. And there's no excuse for this lack of fitting. There's no explanation, except it doesn't actually happen. It's not true. All right. It's just... It's so dismal being in this position, because there's just absolutely so few people who just acknowledge, okay, that's a damn good argument. They really should have to have a counter argument to that. Why doesn't it take 9 times the energy to go 3 times as fast? It's supposed to be true. Why isn't it true? And there's nothing. And yet I'm the flat earther. I'm some sort of moron because I asked this simple logical question. It's clearly failing the experiment. And it fails all of them. And yet I have to make these videos every day, over and over and over again. It's just amazing to me that I can only conclude that you're dishonorable people, because you have to be able to recognize that these are perfectly valid arguments. And the fact that physics has never done any testing, they've never stuck a thermometer in a ballistic pendulum ever, as far as I can tell, and measured any of this crap, proven any of it with experiments. They've evaded doing that. Instead, they just keep drawing it and claiming it, but there's no evidence it actually happens the way they claim it happens. All right, so let's go back to Shakar finally. So he's going to do a ballistic pendulum, and like I said, he's just going to do such a crappy, lame, weak, pathetic job. It's like Feynman all over the place. But he's always like this. He's just doing math problems. He really just doesn't concepts. He talks as if he cares about concepts and people understanding the concepts. But you can clearly see that no, his lectures are just math, and concepts are, clearly not important. Alright, let me just check the chat in case there's no volume or something. Let's see. Have you ever thought about having a debate night like you need to in the old days? Might liven things up a bit. And again, how? I'm not opposed to it, but I'm just saying, what's the debate going to be about? How can you debate with people that won't stay on the subject? I mean, I pointed out all this stuff in the debate with whatever that guy was, right? I mean, I made basically a video describing this circumstance, and all he did was a math derivation. I mean, and that the stupid Valerie Rousseau, what's his argument? He said, here's my mathematical derivation. It says that, force equals distance, and so fuck you. Arrows have more, arrows with a point on them have more energy. I mean, he might as well say that. Because he's just saying, anytime that I increase the distance, it means I did more work. And it doesn't matter that friction is variable based on speed. None of these things matter to these people. So I'm just saying they can't stay on the subject. So how the hell would it work? Not that I'm against it. I'm just saying you explain to me how it's going to work. And I know what I'd rather you explain to me? Explain to me how video responses fail. I mean, the simple argument is obviously I play their videos. They don't play mine. And obviously I don't just play the video, right? Because that one lame guy plays the video, but he doesn't respond to any of the points. So you draw it, and he just waits for you to say something he'd like to elaborate on. But he doesn't deal with any of your best arguments. He just lets them go into the air, and he doesn't respond in any way whatsoever. So what's the point? I'm just saying but video responses are a perfectly coherent way to interact with people. I think it's much better than, frankly, live performance, because you have time to listen to their argument, think about what your counter-argument will be, and make your counter-argument. So why isn't that a far superior method to debate? So you just show me the response videos I've gotten, okay, where they've actually played my argument and explained where I'm wrong. They've drawn it better than me. Draw it better than me. That's their challenge. Has any of them ever done it? No. Have you done it? No. Yeah. Is the entire human population apparently completely incompetent that they can't do this simple thing, turn a camera on and make a video? All right, I'm thinking that you should have a debate with the AI voice function. Well, fuck you. Which seems to be going increasingly realistic. What's the point? The AI is arguing with Wikipedia again. And for what purpose? I've already asked the AI to link me to evidence, and it won't. It links me to some high school experiment that is not relevant. I'm just saying, the whole argument is about evidence. Science will produce none. They're expecting me to do all the experiments. I have to do the Eddington experiments from space. I have to do all these collision experiments because they've never done them. I have to turn the scale sideways. I think it's here. Yay! I found it. I have to do this experiment, right? Because they can't do it. Just, turn the scale sideways, put something on a pendulum. You'll know exactly what its mass and velocity is, and see if you can duplicate gravity with a momentum. And that'll tell you that Oh yeah, that's all this is. You know, that's all gravity does is create momentums. That's all. This measures momentum. Weight is just momentum. Weight is the amount of capacity to put energy into a spring. That's momentum. It's not weight. There's no difference between weight and momentum. Same difference. All right, anyway. Instantaneous weight. Let me just put it that way. It's not instantaneous. That's probably the wrong word, right? Impulse. Impulse weight. Okay, so let's place your car. I guess I can do it from here. Doesn't really matter.
Remember this, elastic, inelastic.
Go a little higher. So he's saying classic inelastic collision, blah, blah, blah. You lose all the energy.
Collision. This is in one dimension. Now, I'll give you a typical problem where you have to be very careful in using the law of conservation of energy. You cannot use the law of...
See, the law of conservation of energy should not matter. Again, it's not about whether you converted it into heat. It's not about whether you convert it into a vibration or some other thing. It's about whether you can take the blocks that went in and find the blocks out. And those things are supposed to be conserved. So there's no excuse for him saying, oh yeah, well, conservation doesn't work. No, it's working. He's claiming the blocks are there. He's just pretending that he can get away with saying, well, I'm not going to directly talk about the heat because I'm not going to measure it. I'm certainly not going to prove it's there. I'm not going to prove that, 2 units of momentum made 2,000 units of heat because it can't do that. The bowling ball's momentum can't be converted into either 2 joules of heat or 2,000 joules of heat, depending on how I do the experiment. It can't do that.
Of conservation of energy in an inelastic collision. In fact, they ask you to check if take two bodies identical with opposite velocities. Total momentum is 0. They slam, they sit together as a lump.
So they don't sit together as a lump. Nothing ever just cancels. So again, even that statement, right, that somehow I take 2 things and they hit each other and the energy is now canceled. There's no cancellation. It has to get hot, has to do something. It's dissipated in some other way, but it is still energy moving in the universe. It's still masses moving. So it's just such a lie. There's no canceling ever. You can only counter. You can't cancel.
They got no kinetic energy in the end. In the beginning, they both had kinetic energy. So kinetic energy is not conserved.
So again, he knows. He's going to just say it with the ballistic pendulum. It's in the air. It's there. It's just heat. So again, why are they claiming that heat isn't a form of energy that you have to use energy to create? You have to use something's momentum, motion, mass and motion, mv, to make heat. You can't make it without using some source of energy, some source of motion. So again, it's just nonsense to say I don't need motion to create heat.
In a totally inelastic collision. In elastic collision, it is. So here's an example that tells you how to do this.
So it's not conserved in elastic collisions by their math. This math won't tell you the truth. That formula is created by creating an equality between momentum and kinetic energy. So they basically say mv has to equal 1/2 mv squared. And obviously those 2 things can't equal each other.
Carefully. So this is called the ballistic pendulum. So if you have a pistol, you manufacture.
So you can do this with anything, right? So you could do it with just any mass that's, say, a 3 mass. It's a bigger mass. And a 1 mass. That's still a ballistic pendulum. And clearly the argument is they're claiming in that case that somehow you're going to create more momentum in the actual motion of the pendulum. The pendulum will actually move with more momentum than you started with. You'll put a 1 mass in here. Might as well use my pointer. Yeah. You could have a 1 mass come in, hit the 3 mass, and their claim is that I'll get 133% over here. So if I make 150. So I have 100% momentum. I have a certain MV, and I'm going to have 150% more momentum, still going in the same direction. Now, obviously, when he's using a bullet example or something, a higher speed projectile, all of a sudden that all disappears. There's no idea that somehow I'm going to gain any kind of extra momentum. They won't argue that, oh, there's more motion in the pendulum. So somehow there's such a lack of consistency in their own theory that in one case where it's just a 1 mass against a 3 mass, there's a huge increase in the amount of momentum I create. But when it's a bullet and the gigantic pendulum that's 1,000 times as heavy, all of a sudden twice the momentum isn't showing up. I'm not going to get twice the momentum into the object. How come? How come it doesn't work with a bullet? They don't say the linear motion of the ballistic pendulum. They don't cut that number in half and then say, okay, let's figure out the velocity of the bullet by figuring out what its momentum must have been. So they're using conservation of momentum, but they're not claiming the pendulum's moving with twice the momentum. So you see the fraud in this? Now this is a high school argument. I suppose I should... I mean, I really have to, I don't want to have to draw everything, but, people aren't too smart. I'm saying, clearly, they have one experiment where they have a 1 mass and a 3 mass. And their claim is the 1 mass goes in with 100 momentum, let's say. The 3 mass will leave with 150 momentum, okay, MV. And now in this case, okay, where he's going to draw it, the momentum, okay, of the big pendulum, the MV, is going to be directly equal to the momentum of the projectile. This linear motion will be the same exact momentum, that is mass and velocity, will be the same as this mass and velocity. So how can they have a theory where as I increase the mass, I start increasing how much free momentum I have moving in that direction, right? So if I have a 20 mass here, a 1 mass against a 20 mass, it'll almost be 200%. Okay, so almost double what goes in. So I put 100 in, I get 200 out. All of a sudden in this experiment with a bullet, there's no idea that I got twice the momentum here. None at all. It's nowhere in their formula, nowhere in their analysis. It doesn't exist. So this concept they say I must believe with pendulums or air carts, all of a sudden when it's a ballistic pendulum, the concept is gone. Where's my Professor Lewin? Here's a sleepless night. Where's the sleepless night? I'm not going to get twice the momentum here. There's no idea of twice the momentum. I mean, come on. All right, it's inelastic. So that's their argument. That somehow, because it's inelastic, it doesn't happen anymore. There's no... This whole concept of this extra momentum just disappears. And it's just bullshit. Because frankly, I think if you do this experiment, you're not going to get that free momentum. But anyway, I mean, you shoot a bullet at a hard object, and the bullet bounces off. You're not going to get more bounce from the bullet, okay? More energy into the object than the bullet plus the bounce of the bullet. You're only going to get the part where the bullet didn't bounce. The momentum that goes in isn't the momentum that bounces off. You throw a ball at a piece of cardboard, the cardboard moves, the ball doesn't bounce back. If the cardboard doesn't move, that's when you get the ball to bounce back. When it doesn't collect any MV. Anyway, continuing.
Back to the pistol. The bullet's coming out of the pistol at a certain speed. You want to tell the customer what the speed is. How do you find it? Well, nowadays we can measure these things phenomenally well with all kinds of fancy techniques, down to 10 to the minus 10 seconds. In the old days, this is the trick people had. You go and hang a chunk of wood from the ceiling. And then you fire the bullet with some speed v0, and you know its mass exactly. The bullet comes, rams into this chunk. So I cannot draw one more picture, so you guys imagine now, bullet is embedded in this. I think you also know intuitively the minute it's embedded, the whole thing is sets in motion. Now you could put this on a table, forget all the rope. If you can find the speed of the entire combination, then by using conservation of momentum, you can find out the speed of the bullet. But that's hard to measure.
Yeah, so we know that this bullet isn't going to give all of its linear motion to the wood. We know that it's going to create a bunch of splintering, there's going to be heat, so there's going to be a percentage lost. And you have to have some idea what that could be. That could be 10%, could be 15%, could be higher. They don't have any, there's no reasoning explaining that you're not going to conserve the momentum in the traditional use of the word conserve, in the sense that it's not going to be linear motion for linear motion. It's going to be linear motion, and you're going to have as a result some linear motion and then some heat. But that's the conservation. You just have to add the heat to the linear motion, and then you have conserved your momentum. And there's no room for the kinetic energy theory.
People have a much cleverer idea. You ram into this thing. This is like a pendulum, so the pendulum rises up now to a certain maximum height that you can easily measure. And from that maximum height, you can calculate the speed of the bullet.
Right. Again, if you make an assumption that it's the same, all the linear motion went into conversion, that somehow it was converted, linear motion for linear motion. But you know, I mean, I'm just saying, you know automatically that you can't even put a nail into a piece of wood without creating a bunch of heat. So you know you've lost some percentage of your linear motion to the creation of the heat. So you're going to have to understand that if you're going to try to make an equality between these two things in terms of momentum. You're going to have to add some extra to account for the fact that a bunch of your momentum was converted into heat.
So I'm going to conclude by telling you what equations you're allowed to use in the two stages. So pay attention and then we're done. In the first collision, when the bullet rammed into this block, you cannot use law of conservation of energy. In other words, you might be naive and say, look, I don't care about what happened in between. Finally, I got a certain energy, m plus m times g times h. That's my potential energy, no kinetic. Initially, I had minus 1/2 m0 squared. I equate these
so again,
two lines.
Says you, okay, so again, it's using two different, he's using momentum at one end and using kinetic energy going in. So what sense does that make?
I found B0. That would be wrong. That's wrong because you cannot use the law of conservation of energy in this process.
So again, the law of conservation of energy should be everybody agree on that energy is indestructible. So you just are looking for where it's going. That heat is energy. It's not something else. It's obviously energy. So clearly, if you're going to talk about conservation, you have to account for where the heat's, what's it's being converted into. And frankly, the conversion is just direction. I mean, the only thing that's bad about heat is it goes in all directions. If you get heat to go in one direction, like a laser beam, yeah, heat's quite useful.
Tell you there's a totally inelastic collision in the middle. Because what will happen is some energy will go into heating up the block. But even
so there you go. Some energy goes to heating up the block. No momentum, just heat, just kinetic energy. So some of the kinetic energy, and it's not some, it's 99.94% of the kinetic energy is not moving the pendulum. It's just heating it. That's their proven result. It's not like I'm making that up. That experiment has been done. All right, so it's just a fact that with the bullet example, you'll lose 99.94% of the kinetic energy is not in linear motion. And yet they're measuring the linear motion to detect the bullet's velocity. Can that make any sense at all? No.
Catch fire if the bullet's going too fast. But you can use the law of conservation of momentum all the time.
So
we'll come to rest on this.
Sorry, yeah, conservation of momentum. It's just kind of funny. They have these different statements.
Times of intermediate velocity is the incoming momentum.
All right, so he just finished the equation, so we're close to where he was. So I'm just saying, it's just such nonsense. You're sitting there using these different terms, conservation of momentum, conservation of energy. You can't do both. Whenever you are converting from one mass to another mass, it's going to fail entirely. You either make free momentum, or you destroy the kinetic energy and destroy the kinetic energy, or you make free kinetic energy and destroy the momentum.
This is like a pendulum, so the pendulum rises up now.
All right, we did that part.
To a certain maximum height that you can easily measure. And from that's wrong because you cannot use the law of conservation of energy in this process when I tell you there's a totally inelastic collision in the middle.
So there's no reason why you shouldn't be able to, right? So if you just measured the heat, then you could use the conservation of energy, he's saying. So you see, to say there's two theories, there's conservation of momentum and then there's conservation of energy. So they're claiming there's two different theories, which doesn't make any sense. You got to conserve energy as a understanding that it has to be both momentum, any form of motion. You have to conserve the mass and the MV. The MV is in both equations, so you have to conserve the MV. Damn. I mean, it's just too ridiculous. You know, for him to say you can't use it, well, of course you can. You just measure the heat in the pendulum, and then you have your answer, right? It tells you how many joules is in the heat, is in the pendulum. So if all you have to do is you measure it and you find 1999.06, I mean 04, I mean, you know, then you know 06, then you know, oh, okay, I can calculate the speed of the bullet.
Because what will happen is some energy will go into heating up the block, but even catch fire if the bullet's going too fast. But you can use the law of conservation of momentum all the time in the first collision to deduce that m plus m times some intermediate velocity is the incoming momentum.
So you know that isn't true, because you know he just conceded it might catch fire. How did I didn't have to use any momentum to set it on fire? Yeah, bullshit, I didn't. Bullshit, you can knock down bowling pins and then still have all the energy of the bowling ball still there, all the momentum. Can't happen. Can't make heat and have the same momentum. Can't happen.
You understand that? From that, you can find the velocity v with which this composite thing, block and bullet, will start moving. Once it starts moving, it's like a pendulum with initial momentum or energy. It can climb up to the top and convert the potential to kinetic or kinetic to potential.
So again, just more talk as if that can happen and it caught fire.
There is no loss of energy in that process.
Says him. So he says no loss of energy. Well, clearly the fire is indication of a loss of energy. I mean, it's just such a bullshit. It's just such bullshit.
Therefore, if you extract this velocity and took 1/2 m plus m times this velocity squared, you may in fact equate that to m plus m gh.
So again, he's just equating kinetic energy to momentum. He's using momentum to decide how fast the bullet had to have been going. All right, because his kinetic energy doesn't, he's going to pretend it wasn't conserved when in fact it was as conserved as the momentum. The momentum has two components. It has the heat component, the part where you use some of it to catch the wood on fire, and then the rest of it went into linear motion. So it's exactly the same thing. There's no difference between the two. The fact is, though, is that there's no evidence that kinetic energy exists, because none of the kinetic energy, more than just the momentum, you don't get more than just the 2 joules of momentum. You don't get any kinetic energy as linear motion. And what, this is another one of these coincidences? It's just a coincidence that in every single case, you can never make the pendulum move with the linear conversion of the kinetic energy. The kinetic energy will never convert into linear motion. It'll fail catastrophically. And yet they'll talk about kinetic energy as if it does work. Well, if that's the example of doing work, that is completely failing to move the object and converting all of the energy, 99.9%, into heat, wouldn't that be the definition of a failed fuel? I mean, if I had some idea for an engine design and the engine made 99.9% heat and only 0.0% motion, you know, would you buy it? Would you buy that car? So this is ridiculous, frankly. It's just ridiculous.
It's last result. In every collision, no matter what, momentum is conserved. Energy may or may not.
There, so you know, in every case, momentum is conserved. Therefore, that's the real thing. Okay, and again, in this case, it wasn't conserved by his description. It wasn't conserved as linear motion. It was conserved as a portion of heat and a portion of linear motion. So it's just so dishonest.
If I give you a problem like this, where in between there's some funny business going on which is not energy conserving, don't use energy conservation from start to finish. Use momentum conservation, find the speed of the composite object. This is what you got.
Yeah, use momentum because it works. Don't use kinetic energy because it doesn't work at all. That's the simple takeaway from this statement he's making. The kinetic energy theory will do you no good. Just like with a rocket, calculating the kinetic energy of the exhaust won't do you any good at all. Because the only thing that's going to move the spaceship is the momentum. The momentum of the exhaust decides how fast the spaceship goes. Kinetic energy, waste of time. Don't even bother calculating. It's of no function. It has no purpose. Because you won't get any of it as actual work. It won't do anything.
But understand in your head, it's not just equation. When can I use conservation of mechanical energy? When can I not? Bullet ramming into a chunk of wood, you better know you cannot use conservation of kinetic energy. But once the combination is going up, trading kinetic for potential, you can.
Yeah, so again, he's just pretending you could catch the wood on fire and it wouldn't use any momentum of the bullet. Only the kinetic energy will start the fire. The momentum won't start any fires. I mean, bullshit. Okay, the end. God, it's just so bad. I have to go over this and over this and over this. Alright, so maybe we'll come back to that if I take a break, or I don't know, see how things go. So I'll just save it for my own purposes. Alright, so this last guy says crank. So that's just a brilliant counter argument, isn't it? Crank. Ooh. Ooh. That's all they got. See? So isn't that just demonstrates the waste of time? You draw it, you explain it, you state it, and they can't counter with a similar argument. They can't show where I drew something inaccurate. Let's see. Yeah, we'll time him out, see how that goes. Give him a day to come back with the same useless piece of shit statement. It's got some sort of little coat of arms as an icon, I guess. Yeah. So only 3 viewers. Yeah, that's not going to work. Ooh, 4. So let's see, is there anything else to say? I mean, I made my argument fundamentally. That's what I wanted to accomplish. Talked a little bit more about ballistic pendulums. Physics is just being duped. They're just fools. I mean, they're being fooled by the pointy arrow. You know, it's really that bad. They're thinking that pointy arrows mean something has more energy. Because the arrow is pointy, it has more energy. Because speed is just doing the same thing. It's just a gimmick. Speed breaks things because all the things that are stuck together, like the skin, everything that's stuck together, it's stuck together because of forces sticking it together, magnets. And the fact is that you can break magnetism by quickly removing something from its condition. It will take less energy. The quicker you can move something out of a magnetic field, the less work you will do. Absolute fact. The quicker you move something through a gravitational field, the less work you will do. And it's that fact, okay, that they're confusing and saying that means it has more energy. It doesn't have more energy. It just has an ability to create a result different, a different result, because it's going to take advantage of a weakness, you know, in a field of force. Take it. Look, I can do it with the light bulb. I can do it with the sun analogy. The sun is shining outside. You go outside. You can move around all kinds of different ways. And the only thing that's going to matter about how much sun tan you get is how long were you in the rays of the sun. So you can understand, the quicker I can move something through, something that was photosensitive, you know, and it would fall apart if it gets hit by too many photons. You know, the quicker I move it through that field, the less it's going to be ruined. You know, the less suntan it's going to get. So speed has advantages. I don't even like saying that, just because so does heavy and slow. So it just depends on what you want to accomplish. You want to knock a building down, you want to use heavy and slow. You don't want to be shooting 6 million bullets at it. I mean, you don't want to be heating the building. You want to give the building momentum. You want to let gravity do the work. Hitting it with bullets, you can't get it to wobble, you can't get it to move. But hitting it with a gigantic weight going very slowly, you can get the whole wall to move, and once it's moving, you can let gravity do the rest. So the fact is, speed doesn't mean more effective at everything. It just means it's more effective in certain circumstances. And slow things are more effective in different circumstances. Heavy, slow things. But really, I've done so many of these videos, it just amazes me how belligerently stupid, ignorant, wrong you people are. I mean, you're just belligerently wrong. Levers work. They convert big M, little v into little v, big M. They work. Pulleys work. They do the same thing. They convert momentums. They don't... Mechanical advantage is just bullshit language, because you can use the mechanical advantage in either direction. You want to lift a heavy thing, you use the quick motion. You want to, do the opposite. You want to launch something into space, you use the slow motion of a big heavy object to catapult, or trebuchet your object into space. I don't know, like I said, it's so depressing. This planet is just so depressing. I just never realized that people are so dumb. So thick. I mean, my father was an engineer, and, I didn't have this good an argument, before he died. I didn't, I had some good arguments, but they weren't this good. And, he did listen to me, so at least he gave me that much. He's a chemical engineer. And, but he really, he just wasn't in any way prepared to concede, okay, they're wrong, because he was just basically saying, well, they can't be wrong, because how could all those smart people be wrong? And it's like he didn't really know the history, that it's not Newton's physics, that it's all, Leibniz and... Huygens, and that it was never proven by experiment. It was just stated as an axiom of life that there's this living force, this hidden scalar energy. They didn't use scalar then, but this idea that somehow it has some sort of sparkly energy that doesn't have a direction, and it's that energy will arise and show up and do work. But clearly it doesn't. In every single experiment, it fails to do any work. I mean, work in the case of the ballistic pendulum is move the pendulum. And it fails to move the pendulum with 99.96% perfection. Its failure is 99.96% perfect. It's such a it's perfectly ineffective. And you people still believe. They'll concede it's perfectly ineffective. Professor Lewin writes the number right on the blackboard. 99.94% of the kinetic energy was ineffective. And you still believe in this crap. That this is the real energy of the universe. Just amazing. Sorry, yeah, I'm just stunned. I mean, I just, I'm just saying, like I said, it's not about you people being dumb. It's about you being dishonest. I mean, how can you ignore all of that evidence? All of that experimental evidence demonstrating this kinetic energy fails to show up to do any work. doesn't move a spaceship in space, completely fails, and yet you're believers. Amazing. All right, so I guess I'll call it an evening, do some other work, watch some other lectures, I guess. But yeah, I really, just you gotta find somebody, a physicist who does experiments rather than just writing this gibberish on the board. And they always do some silly thing like, oh, you want to find out the total energy of this line. Why do I want to know that? And why wouldn't I just say, well, let's just say the plus parts and the minus parts are all kind of equal, so why don't I just draw a straight line through it where, I have the same amount of stuff over the line as I have under the line. As long as I do that, this average will do me just as good. I mean, you know what I mean? You can just mechanically do it. You can just mechanically do rough estimates, I don't need infinitesimally small integrals to get a general idea. Why would I ever need to be that specific? Unless I'm calculating how much fuel I need when I get to point B. But again, in most cases, the path isn't going to look like this. That's not going to be the path. It's going to be some kind of simpler thing, like, oh yeah, I went to point B, then I went to point C. I mean, that's a lot easier to figure out what the average is there. Same about above, same about below. Well, anyway, so they make it all seem like they're doing something worthwhile, and it's all, who needs this? Where are you actually going to use this crap? I mean, you could argue that, you can draw all of it. Like, even if you're doing complex gravity, you can create a drawing that has proportional measurements, a model. And then you can just take a protractor and do measurements, and you get your answers. I mean, you don't have to use their formulas. Not that all the formulas are wrong. I'm not saying all their mathematical formulas are garbage. I'm just saying that obviously their notion that you acquire constant forces like rain or wind or water flow or paint spray or sun radiation, that these are something other than just time-dependent forces, that they don't have any distant dependency. You don't get them in clumps of distance. You get them in clumps of time. They push on you in units of time. They don't push on you in units of distance. Obviously, especially when you're going faster, you're going to acquire a velocity from being pushed, obviously. So maybe I'll just draw that. Yeah, I mean, so many times. I'm just saying that I don't know how an honest person can look at this and say, okay, I honestly don't understand. Yeah, I just don't see how it's possible for somebody to say they honestly don't understand. Alright, so I'll draw these two units of distance in a different color just to illustrate the point. But yeah, you know what's going to happen. These are the same mass. Same mass. Okay, same mass. And so you know what's exactly going to happen. So let's just say this is 4.9 meters, okay, of distance. It's going to be 1 second. All right. And it's going to, and it's going to hit the ground. It'll be going 9.8 velocity. So you know this is exactly the same as this. So you know this is 9.8 meters per second. You know when it finishes, actually, you already know that it's 19.6. So you know this is half your velocity right here. You're going half your speed there after the first second. So you'll have 1 second here, 1 second through this whole thing. Okay, so this whole thing is going to equal 1 second, and this little bit is going to be 1 second. It's only 2 seconds. You know you got 9.8 here. you know you got 9.8 over this whole distance. That's all you got. This whole distance, you only got a 9.8 increase in your velocity. So you know it's only 1 unit of push. It's not 3 units of push. And the simple argument is if I turn the gravity off right now, right here, so as soon as it got to this point, I turn the gravity off. You know you're going to get these 2 units of distance for free. You're going 9.8. That's not going to change if I turn the gravity off. You already have that velocity. So you're already going to get these 2 units for free. That amount of distance. And all you're getting is another this. This is all you're getting. You're just getting another 4.9 meters of distance added. And you've got this increase in your velocity. I mean, you know, if you go in further, you know that this 19.6 means you're going to get 4 units of that. So in the next second, you're going to get 4 units for free. That is, you don't have to do anything to get those 4 units. And you're just going to add 1 more. That's it. Just 1 more is added. Same as here. 4.9. You get the same thing per unit of time. Per unit of time, you just get 4.9 of added distance. And you get 9.8 of added velocity. And that's all you get in units of time. I mean, how can you say that these things here are units of gravity working on you when it's clearly in 1 second units? It's 9.8 meters per second. Meters per second over 1 second. It's in 1 second units. It's not 9.8 meters per second squared. It's 9.8 meters per second of increase in your velocity per 1 second. In 1 second units, it's 9.8. If I change what's down here to a half second, I have to change that to 4.9. If I make it 2 seconds, I have to change that to 19.6. It's in units of time. I mean, fuck. Like I said, you have to be dishonest not to be getting these arguments. This has nothing to do with being dumb. It just has to do with being dishonest. You don't want it to be true. You don't want me to be right. And that's all you have. You don't have anything else. You have 0 evidence. We have 0 response from any physicist. We can't pay them to show up and respond to this argument. Draw this and explain how these 2 free units of distance actually gave you extra power somehow. Somehow you gained 3 units of power here and only 1 unit of power here. Somehow gravity only gave you 1 unit of force here, and it gave you 3 units of force here, even though you're going half your velocity here. I mean, how can you believe this shit? Obviously, like I said, you don't believe it. You just couldn't give a fuck about the truth. The truth doesn't matter. Life is about living some deluded fable. It doesn't have anything to do with the truth. Ugh, God, I hate this planet. 99.9894% lying scum. That's what the statistics indicate. Yeah. Alright, so I guess I'll go. We're down to 2 viewers, so I don't know what it is about Tuesday night, but yes, if Tuesday night sucks, at least this week. So not much I can do about that either. So we'll call it a video and get the hell out of here. Now that's the worst yet, I think. An hour into this thing and I got 2 viewers. Fuck. Yeah, fuck. No point. But it's alright. I was going to make the video anyway, and so it's pretty much the same video I would have made anyway, so we'll leave it at that. No useful contribution from viewers. Alright. So, till the next time and such and so forth and whatnot.